Let us continue. So I went ahead and wrote up some of this we can describe it more. So go ahead and write this down as we go here, or pause it and write it down. So we're going to partition AB and partition CD. So you take A to B and we go through and partition. Similarly for CD. And you get that grid. Okay, so this is the partition that we say. Then the R sub ij is the subregions of R. So they're inside here, right? So those are each of the subregions. So then we just list them out. Basically what we take then is what's called an inner partition. So an inner partition is you just start saying that's 1, that's 2, that's 3, that's 4, etc. And you just keep going, right? So you keep counting them like that. So in other words, they're there, you can just list them out. So then we're going to let R sub k be the set of all rectangular regions that lie completely within R. So it's all within this R. And that's what our inner partition is. Okay. After that setup, we have 1. We define the norm, which I described earlier. The norm of the set of all the R sub k's. And we define it or write it the same way. Norm P is the length of the largest diagonal of each of the R sub k's. And that's how we described that earlier here. You take the longest diagonal, compare this one to this one, and you make that go to 0. So to what happens as we described before, to make that go to 0, you have to basically put in another partition. So once you put this one in, so you can maybe go back like this and say, let's just put in another partition. So if you do this and this, now the partition has changed. That's what's maybe not described, but that's what's changed. So now the largest one might be this one. So now this one is the largest diagonal. And so you got to partition that again. So everything is shrinking to 0. So the issue was how you want to define this. If you just have something go to infinity, then you could partition just one side, like just this thing right here could go to 0 or go to infinity. You just keep on going here. You need all of them to start approaching 0. So that's why it's defined this way. Okay, let's get on to some problems, huh? Let's continue the definition. 2, oops, let me change colors there so you can actually read it. So 2, we're going to let delta A sub k denote the area of R sub k. So it's the area of R sub k. Then we're going to choose the U sub k, V sub k in R sub k. And it's just like the interval, some arbitrary value inside of it. 3, we'll define P, the partition, to be the set of all the R sub k's. And then we define the Riemann sum. So a Riemann sum of F for P is the sum over all the k's of F of U sub k, V sub k, delta A sub k. And then we let the norm of the partition approach 0, and you get the limit and how it's defined. So for 4, let f be a function of 2 variables defined or in R. Then the double integral of f over R is defined to be this. So you say the double integral over R of f of x dA is equal to that limit. So it's the limit as the norm of the partition approaches 0 of the sum. So it's the sum over all the k's, f of u sub k, v sub k, delta a sub k, provided the limit exists. It's provided the limit exists. So let's look at that picture, what that looks like. So basically, that limit exists if f is continuous on R. That's one of the theorems. So the theorem basically just states that. Says if f is continuous, the limit exists. And then we say also if f, oops, forgot the f part. If f is continuous on R, then f is integrable on R. And let's draw in our picture this time. So draw an axis. So this is kind of more what it looks like and what you can be, kind of asked. So if we look at this as a function like this, so we have some function up here. This is our arbitrary function shape, like that. So we'll call that f. And then we have our region down here in the xy plane. So that's my R. Then when you integrate over this region, right, you're going to partition that up, take a limit. So it becomes continuous, infinite. What I normally do too is make this dotted here. It's just dotted. So these are dotted lines like that. Make it a little better. Still try to do this as if I'm right in class, as I'm trying to anyway. What you get are these rectangles in here, and then the height is the function. So you have these rectangles, and you go up to the function itself, and it gives you this height here. So you get volume, right? So as you're adding up all these things, you have the dA is down here, the delta A is that, and then times the height gives you area times height. And so then you add all these up over the entire thing, and you get the volume underneath the surface. So the double integral over the region of f of x, y, dA equals, oh shoot, not area, but volume. So it's volume, assuming, of course, f of x, y is greater than or equal to 0 for all x, y in your region R. Right? That has to be true, of course. And it can be other things. It could be other concepts. Now, if your f is equal to 1, then what'll happen there? So basically you're looking at all these little areas being added up right here, and you have another area and another area times the height. But what if the height is 1? And you're adding all these pieces up. What do you get when you partition this thing? You get area of the region. So that double integral, if f is 1, is just the area of the region. All right, so now, so that's the theory. That's all the conceptual stuff in the theory, what the limit is saying in the partition. Now let's look at actually taking some iterated integrals. So this is, actually some of the problems. So let's look at some of that stuff. We'll do that, do a few of those. Looks like I got one good example, then we're going to go on to the general region, and I'll just do another video for that. That'll be 15.2 and 15.3 kind of together. So let's look at this one. And this will be a rectangular region we're integrating over. So it'll match this, this setup back here, defining that region. So this will be the rectangular region case. So let's look at this example. So iterated integral, evaluate the double integral, and this goes from inside is -1 to 2, and then 1 to 4 of 2x plus 6x squared y. And then this says, this is kind of important, which direction. This is dy and then dx. So the way we are, so remember how you, with partial derivatives, you had to say which one you're doing first. So this is the same idea. You go inside out. So the first you're going to integrate now with respect to y. And then these are your limits of integration for y. So this goes, y is from -1 to 2, and then y goes from, or then x goes from 1 to 4. So our region is defined, and this is what you got to pay very close attention to. Your region is defined by those. Okay, and that's the most important part about most of this stuff. So if we draw on our region first, I don't really care at this point what the function of f of x, y is. It may give us volume, may not, but it's just an integral. So this is saying y is from -1 and then to 2, and then x goes from 1 and then 2, 3 to 4. So what you get is this region here. This is what you're integrating over, like this. So that's my r, and this is the kind of the only case we'll do, or example, that it's a rectangular region. Otherwise, next we're going to put in functions here and here. Okay, we'll get to that next time. So this is what we're integrating over. So this is our region. All right, so let's continue. So that's, we say that equals, then it's the outside integral from 1 to 4, and then we integrate with respect to y. So you can put in your brackets like this, and then you do each one of these, right? So it's just 2x, and so it's just a constant, so you get just y. And then this with respect to y, add 1, divide, makes this a 3, and then y squared. All right, so you should get 2xy plus 3x squared y squared. And then when you're starting like this, again, mentally, go back mentally go back and do a derivative or a partial with respect to y and see what you get. Okay, so this, and let me move this down a little bit, kind of in the way. So this is evaluated from -1 to 2. Let me say dx. So now you want to evaluate that before you take the next integral. You want to substitute that in and then keep going. So what you get then is, and it'll be a little longer, so I'll bring it down here, is equal to the integral from 1 to 4. And then let's substitute in the values, and you get 4x plus 12x squared minus, and then substitute in negative 2x plus 3x squared dx. Okay, and you keep going. Integral from 1 to 4. Simplify that, just so distribute the negative and simplify, combine like terms. You get 9x squared plus 6x dx. And then now you're back down to essentially just single variable stuff. So I'll let you finish that, check that, and you can pause it and do it later or whatever, but you get 234. So that was going dy and then dx. So now what I want us to do next is do the other order. So what if I wrote it like this? And this is just kind of prelude to what we'll do next. Suppose then you had the double integral from -1 to 2 and from 1 to 4. So now I'm going to switch the order now. I'm going to say dx dy. But it's still the same function, 2x plus 6x squared y dx dy. All right, so take a moment to do that. Pause the video and such. So now integrate with respect to dx, right? So you do dx first, or integrate with respect to x first, substitute in your values, and then integrate with respect to y and evaluate. What do you think you're going to get before you even do this? Okay, so pause it and try it. So you have seen that you get 234. You get the same thing. So is that a coincidence or not? Most of you probably guessed that that is not a coincidence. So the order doesn't matter. So that's called Fubini's theorem. Basically, remember how the order of the partials didn't matter? Well, the order of the integration doesn't matter. So just roughly, if you go A to B, C to D, and everything's nice and continuous and differentiable or integrable and all that, you can switch the order. So and that'll be true for when you have a general region, which will be functions going back and forth. So this is called Fubini's theorem. Don't need to know the name or anything, but that's what you can do.